Let me just do a little bit of a poll. Has anybody used anything from Project Loom at all? Virtual thread? One person, a couple people. Okay, cool. And then who's using what version of Java? If are anybody using 22 at all? 22, 21, a couple of people. 17?
17.
Mostly 17. 11? 8? Okay, cool. We got it. And I'm not going to ask about before that because it's like it's super embarrassing. I'm not judging. Hi, my name's Todd. I work here at DB. I'm the director and the lead engineer on payments for CD for the Cary office. I've been working professionally with Java for 29 years, and I'm helped organize JUG here. I do have a co-author for this presentation, but it's his dinner time, and he's not allowed out of the house during dinner time, and he can't make it. This is my dog, Charlie. Every time I work on a little section of his talk, I take Charlie on a walk and explain virtual threads to him, and he's like a really good listener, so I felt that he should get some credit. And if he were here, he would love all of you. So, but just a little level setting of what we're going to talk about today. And if you can't hear me, just give me the thumbs up, tell me to speak louder. We'll have an overview of Project Loom, of where does all these other projects fit in structurally. And then we can't really understand structured concurrency and scope values without understanding virtual threads first, so we'll do that first. And then if I could just ask that you save questions till the end, I'll answer any questions you have at the end, okay? So let's talk a little bit about Project Loom. So I'm not going to read this whole to you, but this is the project charter for Project Loom. And this is the part that most people tend to look at. This is the easy to use, high throughput, lightweight concurrency. But there's this other part down here, which a lot of people miss. And that's mostly what we're going to be talking about today. And we miss it when we talk about Project Loom, because if we graph out what Project Loom has in it, and you zoom way in, you'll see there's two other projects on here. There's Structured Concurrency and ScopedValues, and they're really small. They're right down there. And that's what we're going to be talking about today. So in terms of where does Project Loom fit, I've drawn this graph here. This is by Java version. So Loom started right before Java 10 in 2018, January of 2018. They've been working on it for quite a while. They're still working on it. Virtual threads were previewed during 19 and 20 and were released in 21. So if you've got Java 21, you can use virtual threads. There's a couple little issues with that, so you probably want to be careful. But they work, they're great, they're fantastic. Structured concurrency, which we'll see, has been incubating for 2 releases and preview for the last 2 releases. ScopedValues incubating for 1 release, preview for the last 2 releases. And then I have been diligently checking the Java 23 page literally every day. They have not announced what either of these 2 are going to be in 23, so it's either going to be preview again or released. They haven't made any changes to the documentation, so the JEP, the Java improvement process, for either of these in the last preview round. So there should be, hopefully we get this in 23 and they'll be finalized. So let's talk about virtual threads, because we can't really understand the rest of this without understanding virtual threads. So when you have a thread in Java, you're basically wrapping an operating system thread. Every time you ask for a thread, you have to go to the operating system and say, hey, can I have a thread? And if you're on Linux or Mac, there's a fixed number of these per process, like 4,000 or so. There's a fixed number, right? And Windows will basically just keep giving them to you until the operating system runs out of memory, which is probably not a great idea, but that's what it does. The problem with this is that each one of these, it takes time to go and do that. You're reserving an operating system thread, and you have to allocate a unknown amount of memory, because we don't know how deep that stack is going to be. So if you're a Java developer, you're probably used to some pretty long, deep stack traces for certain frameworks. And that memory for that stack and all the variables in it has to be reserved at the operating system level. And so this works fine, but it's there's just a fixed number of them. We can't go crazy with this. So this is a brilliant diagram of a platform thread. Time in this model goes from left to right. So if you're doing some work on the platform thread, that's fine. You're working, you're using the CPU, the thread is actively being used, the operating system is doing what you need with that thread. But if you go into a wait state where you're waiting for bits from a network or a file to be brought into memory or something like that, or sleep or something where you're waiting, this platform thread is taken up with that work. You're not doing something useful with that thread during that period of time. So this part where you're waiting is suboptimal. You're not doing any useful work during that period of time. So the problem with these threads are they're memory hungry. They have a slow creation time comparatively, and I'll show you a demo of what I mean by that. They're completely useless when they're blocked. There's an overhead for context switching them. So in the operating system, when you have a thread doing some work and it's some other thread's turn, the operating system has to take that thread off the processor and put another thread on there. That takes time, and I'm grossly simplifying all of this, by the way. And then, as I mentioned, there's a fixed number of these per operating system. So let's talk about virtual threads and how this changes the model. If we expand our view here, and instead of platform threads, we call these carrier threads. So a carrier thread, still tied to an operating system, it's still conceptually like a platform thread, but in this model, virtual threads, these are just created on the heap. We can create these instantly. We don't have to set aside special memory because we can grow that memory that the stack takes up whenever we want to. We can create these virtually no time at all, and it's all on the heap. And these threads take turns mounting to the carrier thread and coming off of the carrier thread when they don't have work to do. So in this at this time of your application running, maybe these 4 threads are taking up carrier threads, and then you have other threads that need work and they mount onto the carrier threads. Just want to note that you can't, as a Java developer, know that carrier thread. You can't do anything with it. You can't figure out which one you're on. It's completely irrelevant which one you're on. They're all identical. You won't have any visibility into that. And this diagram, I think, explains how the virtual threads get mounted and unmounted from the carrier thread. I'm not going to go through this in super amount of detail, but as you can see, virtual 1 has some work to do, so the carrier is mounted to the carrier thread. And when its work is done, when it goes into a wait state, the Java virtual machine finds something else that needs to be done, so virtual 2, and that work is mounted onto the carrier thread, and then virtual 3, and then back to 1, and then 3 and 1 and 2. It doesn't, this at scale with potentially thousands or even millions of virtual threads is what's happening under the covers. So you're still, as developers, using these threads like you would other threads. This is just what's happening under the covers, and it's a much more efficient use of the operating system's resources. So back to this, if you want to create platform threads, you can still do that. There's cases where you would not want to use a virtual thread, you'd still want to use platform threads. So you can still do that. And I want you to start thinking of virtual threads as tasks, not so much as threads, because you're going to create them, you're going to use them, and then you're going to throw them away. Because it's basically free to create them, so you don't want to pool them. You don't want to keep them around for very long. And with that model in mind, I want you to think of virtual threads as basically unexhaustible. You can create as many as you need. You'll never run out of them. And you, as a consequence, don't pool them, okay? So what does virtual threads give us as a summary? Still the same API you love with Java Lang thread. I'm assuming you all love this API, right? Much lower memory requirements because you're creating them on the heap. You're not having to go off and reserve, a megabyte or whatever of operating system memory for a stack. You can create them practically instantly because it's just, JVM is very good at object creation on the heap, and it makes better use of system resources. Those carrier threads are used at almost 100%. We don't have a one-to-one mapping of virtual thread to carrier thread. There's more than one can be assigned. So let me show you what I mean by the quick creation time. So this is just, can we all see this? Do you want me to make it a little bigger? Is that good? Good, okay. Little housekeeping of what I've got in here. These 3 methods will come in later. Log is literally just a log statement. It's just printing system out println. Don't tell anybody I'm doing system out println, especially if I'm reviewing code for you here at UV. I wanted to point out that instead of using the name of the thread, I'm putting the ID of the thread. Virtual threads don't get named by default because they are, create it, use it, throw it away. There's no reason to name them. They all get numbers, so I'm just printing the numbers in the log. There's nothing really fun about this method except I just wanted to show you. The main method, also not all that fun. It is just creating a platform thread and calling this function go, which we'll implement in a second in a bunch of different ways. And so basically just remember that Go is itself running in its own thread. So let's see how long it takes to create some threads. So we'll do current time millis. We're going to time this, and then we're going to say so we're going to say, let's say we're going to make and I'm sorry this is a little jankety with the keyboard. My new computer died last week, and so I've had to pull my 8-year-old gaming laptop out of storage and frantically update everything, and half the keys are like really sticky on here, they don't work, so bear with me and I appreciate it. So if we create like 5,000 threads, okay, we're going to say map to object, and we're going to call this I, and then in each one of these we're going to say thread.ofPlatform. Now this is a new builder that's coming on Thread. There's a new builder, you can set anything you want about it, whether it's a daemon thread or what group it's in, or its name for platform threads. You could set names on virtual threads if you want to, they're just not named by default. Priority, stack size, all that nonsense you're currently able to do, you can do with this builder. I'm just going to start this. I'm not going to do anything fancy. And we're going to say, let's write the worst clock we can. So we're going to create a clock that is 5,000 seconds long. And each thread is going to do, so it's going to sleep for I number of seconds, and then it's going to print out the time. So each second in this clock has a dedicated thread that waits until its specific time to print, and then it prints it. This is the worst way to write a clock. Don't write a clock this way. I'm just doing this for demos. Also, you want to handle exceptions. I'm just doing demo code, so I don't particularly care. And then we want to do, I could never remember that, so I made IntelliJ remember it for me. And then we're going to say toList. This is, now we have a list of threads. This is also another nice function. This came in Java 16, I think. So instead of doing a collect on a stream, you can do it, instead of doing collectors.toList, you can just say toList on the end of a stream, and it'll give you an immutable list.
Yeah.
Yeah, exactly. It's like the reason enough to join to move to Java 17 right there. Okay, so now we've got some threads. We're going to say system out println. Again, if you don't do this, use a real logger. We're going to say how much time it's taken. And then we will run our we'll join it. So join means just wait for the thread to do something. Wait for it to finish and then continue. So we're just waiting for the threads in order because we're running them in order. And so when we run this, we should get the worst clock in the world, and you can see how long it'll take to create 5,000 platform threads. Now on my Mac upstairs for work, this doesn't fit. This doesn't work. I run out at 4,000, but because this is Windows, it'll give me whatever. And so now I've got my clock running. Again, don't write a clock that way. But it takes about, just under a second to create 5,000 virtual threads, platform threads. So if we want to do, like 15,000, now we're getting up there. It'll take a little bit of time. So just over 3 seconds to create 15,000 platform threads. And again, Windows is just giving me as many as I want in this. It's not a real great strategy to keep doing that. But if we switch this to virtual, we do virtual threads instead, we can create 15,000 threads in 155 milliseconds.
Nice.
And it gets better. I mean, we can do a million. And the JVM will do it. It'll do it really quickly. So it does it in just over a second. 1 million virtual threads. You're never going to run out of these. You can create them and use them and throw them away. Okay? We'll do that. Okay. So now that we've seen that, I want to talk about the project charter again. Mentions high throughput. High throughput is what the virtual threads give you, and they give you that because of Little's law. Has anybody heard of Little's law? Okay. Let's pretend we're running a store, like a physical, actual store that you can go to get things. And this is a regular store that has a regular flow of customers. It's fairly consistent. So the arrival rate. So let's say we have 10 customers coming to our store every hour, and they spend, let's say, 30 minutes in the store when they go there. The number of people we should have in the store at any given time is 5, more or less, okay? So this is what Little's Law does. You can apply this to queuing theory, you can apply it to threading. So with the magic of mathematics, we can say in a stable system that arrival rate is like throughput, and we can solve for throughput. And so the only way to increase throughput in an application with Little's Law is to decrease latency or increase concurrency. And because of the number of virtual threads, that's what virtual threads are giving us, is an increase in concurrency, which gives us an increase in throughput. Which I think is interesting as to why is it working. So final thoughts on virtual threads. Don't pool them, seriously. Create them, use them, and then just throw them away when you're done. You don't need to pool them. So the other thing that comes with this is don't use pools of threads as a way of limiting concurrency of other things. Like, I only want 3 connections to this other resource, this other API that I'm talking to, so I might have, in the past, had a thread pool associated with that. Don't do that. Start moving to a model where you have a latch or a counter or something like that, a thread safe thing. Java provides you these tools. I'm not going to go into them, but start thinking about those things. And be open to new ways of writing concurrent code. So places where you wouldn't have made something concurrent in the past because it's a pain in the neck to take up a thread or do all these things, be open to the idea that now you can do more concurrent code in more places where you probably wouldn't have done that before. So now that we have a base understanding of Loom and virtual threads, let's talk about structured concurrency. And you can't really talk about structured concurrency unless you talk about unstructured concurrency first, so we know what we mean. So back to the demo. We will erase all our glorious code here. And we're going to write some concurrent code. Now there are a lot of different ways to write concurrent code. I'm just going to use futures, okay? With an executor service, I understand you can use completable future, you can do RX Java, you can do reactive, you can do lots and lots of things with callback hell. I'm just doing futures because it's easy to demo, honestly. Okay, so we're saying var f1, which is just going to be future 1, and yeah, I'm using var because I'm too lazy to type out future of string. Backing up, let me talk about these 3 methods I've got predefined. So succeed eventually takes a time, like a duration. We sleep for that duration, and then we just return some very important data. So I've got another class called very important data, and all it is a list of Simpsons characters. Super important. So we just get one of those off the list and return it. Okay, that's success in our model for the example code. Failure is similar in that we sleep for the duration that we ask it to, and then we throw in a legal state exception as a failure. Now you'll see I log when we interrupt, because we'll do some interrupting later. And then tick is somewhat interesting in that we just sleep 1 second, print out tick, and then just do that forever and ever and ever and ever and ever if we wanted a thread that just kind of runs forever without end. Okay, so when you see those, that's what those mean. So we have an executor service up here. It's just a fixed thread pool, and we'll say executor service dot submit, and I'm submitting these as runnables. You could do them as callables or as what's the other one?
Lambda.
I guess you can. I thought you could do suppliers, but I guess not. Scope values you could do suppliers. Okay, so we're going to say submit. We're going to say succeed eventually. And I like using durations where I can. I don't like just assuming everybody understands that this is milliseconds. So again, if you want to appease me on code reads durations. And we'll just have one take 2 seconds and one take 4 seconds. So these 2 jobs we are submitting to this executor service, and then we're gonna print out the answer of both of these things put together. Okay, nothing super exciting. So we'll say f1.get. So we're waiting. There's a future being returned, and we're saying wait here for the answer that it returns. The other part about this laptop being broken is that the trackpad is super sensitive and I cannot turn it off. So I'm typing super oddly. So anytime you see the mouse move, that's the laptop and not me. probably. Okay, so we just go and get these two. We're going to run this. It's not going to be all that exciting. I'm just showing you the success case before we start showing failure cases. So we have thread 24 about to succeed, thread 25 about to succeed, and then we get Mona Simpson and database, who are two Simpsons characters. Okay. So let's do something fun here. Let's take this and ramp it up to like 10 seconds. We'll succeed in 10 seconds, and then we're going to fail here. So what happens here? We run this. We'll see fail happen. We'll see an exception because that method that we called go is done and gone. We can't do anything with that now because an exception just bubbled out of it, but that success thread is still going. It's still going. We've bled that thread out of our context, and it's running longer than the parent is running. So the child thread is running longer than the parent thread. This is a problem, right? Now, we could fix that. We could catch it and we could do all sorts of stuff. We could actually, and at worst, we're just wasting time, right? Because that fails. We know the success arm of this. We know once this fails, we know we'll never need this. So we could cancel that work and be more optimal about how we're using our precious threads. But that's work for us. We have to do that. We have to figure out a way to do that. The other thing we could do is, in Java 21, they came up with this thing, a try with resource. So we'll get similar results in that the success will still go while fail is happening. But because we're putting that in a try with resource, that exception won't come out until the very, very end. Better, we're just wasting time. We're not causing a child thread to outlive its parent, but it's still a complete waste of time. Now, I'm not going to write this code. I really tried to find a succinct way to show you what a pain in the neck canceling one of these versus the other would be. But then I realized, well, if I have 3 of these, then it becomes really, really difficult. So we can do these things as developers. We can cancel these work. We can find out which ones don't work and cancel the rest of the work, but it's such a pain in the neck to do. The other thing that doesn't work well with this model is what happens if the thread that go is running in gets canceled. So let's say down here, T1 is that thread. We'll sleep for duration of milliseconds because we don't really need to stay around that long. We just want go to start and kick out its 2 child processes to go. And we'll say T1.interrupt. And 7 o'clock on Monday means trash cans need to go out. So let's hope I remember that when I get home. And then we'll say, we'll print out just so we know that we've interrupted. So we'll prove that T1 thread is interrupted. So what happens when we run this? Basically the same thing as last time. Now, I would expect that method go to what I would want is when it gets interrupted, all of its child processes to get interrupted as well. And they don't. As you can see, we still have the same problem that the cancellation doesn't bubble down to the children. We'll use that again later. Let's go screw that. Okay. The other thing I want to show you is one last time that there's no real relation with these. So we think, and when I'm talking about this here, that we have parent threads and child threads, that there's some relationship between them that the VM tracks and understands, and that's just not the case. So we'll write public void child. We can even take it into executor server. We'll take in the same executor service to make it really clear that these are not. So we will just call tick. Okay, so we're passing the executor service down to a child function that kicks off another task called tick, and I guess we'll wait for it over here. Probably should have made that return string just to make life easier. Oh, it likes it. Okay, so we're going to run this. This is not fun code. So tick is still going, that thread is still going. And so what we're going to do is go to the terminal. And we're going to say, show me all the Java processes on this machine. An example is running in process 16464, so we're going to say J, CND, 16464. This is another new thing in Java 21. You can take a thread dump and format it in JSON instead of the old standard plain text thing that you have to write a special parser for every single time you want to do something with it. Now you can get it in JSON and use any number of off-the-shelf things. And so this is unstructured, so we'll just call this JSON. Nothing fancy. Not. I didn't clean up the last time we did this. Okay. Unst2. Now we can kill this. And I want to show you so we have our child thread here. There is no parent thread to that child. There's just a container, which is a thread per task executor. So you can see it's just what you expect. There's a run. You don't even know. There's nothing even that this came from the go function, right? And there's go function here from thread 0. There's no indication that it has any children at all. So this is a complete fantasy. These relationships do not exist in Java. I hope you appreciate that I can barely see this because I'm using my glasses so I can see you, but I don't need it for this, and this is very blurry, so I hope you'll appreciate that. Oh, the other thing I wanted to show you is we can do a virtual thread pool now too. New virtual thread per task executor. I probably should have shown you that before. Instead of pooling threads, it's just going to create you a virtual thread every time you submit a task to it, and it's going to throw it away when that task is finished. So if your work lends itself to that, do that. Okay, so now we know how terrible unstructured concurrency is. Let's talk about the problems. The relationships, again, between task and subtask, they don't really exist. There's no parent-child relationship. There's no way to track that unless you manually do it yourself. And as a consequence, observability is difficult. If you have had to look at a thread dump, figuring out what work has happened where is difficult if you have a multi-threaded system. And then managing work is difficult. If we had written code to cancel work that we didn't want anymore, that would make the purpose of what we had written really opaque. Like I just boiled it down to we're submitting 2 tasks and we're waiting on the answers. But if I have to do cancellation and waiting for interrupts, and it just adds more and more and more code. And now I'm in the business of managing threads instead of the business of actually submitting work to a pool to get some work done. So let's talk about structured concurrency instead. Structured concurrency, I was really surprised when I was writing this talk how new this concept is. It only came out in 2016 as compared to structured programming, which came out in like the 50s, right? It's basically every program that anybody here has ever written outside of assembly has been some kind of structured program. So I was really surprised. You can do this in Kotlin and Swift and Java. This is in preview, but it's becoming a thing. It's becoming a way that people talk about structure, like about concurrency. It makes it easier. So what is it? Subtasks have well-defined entry and exit points and strict vesting of lifetimes. You cannot have a child task outlive its parent task. So this is an ideal scenario. This is code. We've probably all written something similar to this. It's just a method called do something. It calls the first method, it gets a result. It calls the second method, it gets a result. It puts those together and it returns them. Nothing, I'm not trying to trick you. There's nothing fancy about this. So when we run it, first method is run first. And we understand this. We understand where it's coming from. If we look at a stack trace, we understand first method is called from do something, line 22. And that, in turn, is called from the main method. We understand where this came from. We understand how this control flow came through the system. Similarly, second method, that gets run next, and then return happens. Now what happens if first method fails, throws an exception? What happens? Anybody? Tell me anything. Just shout it out. There's no wrong answer here. I guarantee you'll get it right. Nothing. Nothing else happens, right? You know these won't happen, okay? So that's what structured programming gives us, and that's what we want structured concurrency to behave like, ideally. So again, this is a bunch of text I've copied and pasted from the JEP on structured concurrency. This is the interesting part. Promote a style of concurrent programming. What I'm showing you is just an addition to the Java standard library. This isn't to change to the language. You don't have to use it. If you like the pattern that it's doing, you can write your own structured concurrency library. This is just a way to do concurrent programming, and Java is providing a reference example of it. And the other goal is to improve the observability of concurrent code, and I'll show you what I mean. So how does it do all this? We have this notion of a structured task scope. So we have this beautiful gray box that's the scope, and we submit tasks to it. And those tasks will be executed in virtual threads. And we wait for those tasks. We say we join on those, join the scope on those tasks. So wait for everything that has been submitted to that scope to finish. And then let's suppose they're all green, they're all good, they all finish the way we want them to every time. And we can interpret the results. Once join is finished and it returns, we understand everything that the scope has been, everything that has been submitted to the scope has finished one way or another. So we can interpret the results. Now what happens if that task troublemaker here on the end doesn't finish correctly, throws an exception, something like that? The scope can cancel those other tasks for you automatically. And then you can throw an exception, you still get to the join point, you can throw an exception there or whatever. What I'm going to show you is in preview mode. If you want to use this, you need, at least the version I'm doing is Java 22, and you need to run it with enable preview. So let's solve those problems that we just looked at. So everything is in a try scope, a try finally, or a try with resource. So we'll call this scope, and we'll say structured new. I'm using Java, not Kotlin, I always forget the new. Structured task scope, and then there's several different versions of this. So we'll say shutdown on failure. And so what shutdown on failure does is it says anytime any of the tasks that I'm submitting to that scope fails, shut down all the other ones and fail. So we'll succeed the first part. So we'll say scope.submit. Now I'm using F1 just to keep it familiar. It's not going to return a future. It's returning a structured task scope subtask, but I don't want to type all that out. It used to in earlier versions. If you saw the earlier versions of this in Java 21, it does use a future, but they changed it recently because it doesn't. You don't have the same guarantees that you do in future, and structured task scope subtask provides different things that we probably won't get into. So we'll say succeed eventually. Duration of seconds 2, and we'll copy and paste, and we'll say 4, and F2, and now here we need to do scope.join, and then we can also do throw a failed. So what that does is it says wait for all of the subtasks that you have submitted to this scope to either complete successfully or fail, and then if they have failed, throw an exception. So when I get down here, I can do anything I want because I know F1 and F2 have not only finished, but they have succeeded because I haven't got an exception. So these look like features, but they're not. So we run this, same as before, nothing fancy. We're going to wait 4 seconds, and we're going to get 2 answers. We're going to get 2 random Simpsons characters. We're going to get Waylon Smithers and Homer Simpson. Lots of funny episodes with the 2 of them. Okay, now let's do some fun stuff. Let's fail. Let's call this to fail, And it doesn't even matter what happens with how long this is. We could set this to 100. It doesn't even matter, right? So we're going to run this, and what's going to happen is the scope is going to detect that F1, the first arm of this, has failed. And it says, if you see this thread ID 24 is about to fail, 26 interrupts that success arm. That long-running 100-second part is interrupted because the scope has understood that work is completely useless. I don't need to wait for it. I'm gonna let that fail, and then we throw that exception. You can see our intentional illegal state exception thrown. So we didn't have to manage anything. We didn't have to do anything. It just did that for us automatically. I'm not losing any threads. These can't outlive their thread. And again, if I don't join there, it won't even let me run this. It'll fail. It says owner did not join after forking subtask. So you can't really use this incorrectly, which I like. I like it when the easy thing and the right thing are the same thing. I think this is nice that it forces you to kind of do it the right way. What do we want to do? We want to show what happens if I interrupt this. So I'm going to say this fails in 20 seconds. We won't even get there. But we're going to interrupt, resurrect this code, run it, and you probably guess what's going to happen, but that interrupt, these two things, why that said false, but that's interesting. Yes, okay, that's the solution to every problem, just run it again. Woohoo! I can't tell you how many times that's worked in my career, by the way. But what we see is that thread that Go is running in is interrupted. The two that scope understands, I've been interrupted. I can kill all of the work that has been submitted to me. So those two are both interrupted. Threads 23 and 25, and fail and succeed. So that's that. That's nice that gets handled for you. You don't need that anymore. And I want to show you the child case. So we only need one. Call child. Right child. Child will get its own scope. It doesn't really matter. You can pass the same scope, but that in a second. I want that to tick forever because we're going to go get another stack trace, and we just want this to hold it. We just want to hold this work open. And we also don't care about exceptions. Don't do this either. We're just making the type checker happy. Okay, so we're going to run this. It's going to create that Go scope. The thread Go is going to run. It's going to create a scope that's going to create a child scope. Okay? Super exciting stuff. So you should see this ticking along in the background. Now if we go back to the terminal, clear this a little bit, and say, give me all the process IDs. 22068 is example. To file. Created the file. Don't care about this program anymore. And what do I call it? TR2. I can barely see that. Okay. Put my glasses on anyway. Okay, so let's find it. So if we find child, we can see where this came from, by the way. We can also see that oh, we want tick. Screwed it up. We want tick. Okay, so tick is running from child, and we can see that its parent is this scope specifically. So 2E1B, and we can see that as the main go scope that is calling child, and we're waiting on that join at that point. So we can see there's a specific relationship between those two threads, between the parent and the child. So debugging that becomes a lot easier because now we have a relationship, a specific track relationship, which is a nice big benefit for structured concurrency. So remember these three things. There's now an explicit relationship between tasks and subtasks. Observability is easier, as we just saw, and managing work is easier because I don't have to do anything to cancel that work. Now I did show you this shutdown on failure scope. There's also shutdown on success. So shutdown on success is when any of these succeed, kill all the other ones off. And you can use that for, there's a resiliency pattern called hedging. You can, if you've got two routes to the same system, you can fire off two requests to it and just take the first one that comes back successfully and then throw the other one away. That's pretty common, and like Netflix uses that all over systems where you have multiple routes through a network to a system, or you have two identical services in two parts of the country, two regions or whatever, that do the same thing. You may want to do something like that, but you can just say shutdown on success, and that'll do the same thing. If you want to write your own structured task scope, you can just subclass structured task scope. Like if you want to say some of these tasks are optional, I don't care if they fail, but I want these other ones to succeed, or I want to, if one fails, immediately run its backup. You can do something like that. You can order results. You can do whatever you want. Java is just currently only shipping with shutdown on failure and shutdown on success. You can also just use structured task scope, like just that one. You won't get any of the cancellation. You can manually do all of the investigation that you want. I don't know that I would actually do that, but it is possible. Okay. Scope values.
Is it possible to continue on a failure, like shut down on a failure? You want to process the other?
Yeah. Sure. Yeah. The question was, can you continue on a failure? Yeah. You could write one that does that for you. I just showed you the interesting one where it kills all the other work. But if you run your work in that bare structured task scope, it'll do that. When you hit the join point, it'll give you all the futures, and it'll say some of these may have failed. You can check that yourself. So you can check the subtask to see did it succeed or did it fail exceptionally. So you can do that. I just didn't remember. Scope values. Has anybody here used ThreadLocal? It's been Java since 1.2. I know you have. Raise your hands. You're all guilty of this. You're not guilty of it. So if you haven't used it, it's like a map where the key is it's like a static map where the key is a thread and there's some value associated with that thread. And we, as developers, use this for caching or a way to limit concurrency. So if I put an object in that thread that is not thread safe, I can guarantee that it is thread safe because this is the only thread accessing that object. There are better ways to do this. Don't do this. Even if you don't use scope values like I'm showing you, don't do that. There are almost certainly better things that you can be putting into ThreadLocals, because ThreadLocals have a lot of problems. Namely, let's see how they work first. Okay, so we've got this ThreadLocal, it's a type string, and we'll call it access level, right? And so this is like an access level set per thread in a thread per request model. So your API receives some request, and that same thread handles it for the rest of the time with us, right? And we've all done this. Spring works that way out of the box. Every EJB container you've ever used works out of the box that way. Basically, this is how thread per request works. So when we use the access level, we set its value. So in this case, we're setting the access level to guest, and we get the value somewhere else. Okay, as long as it's that same thread accessing it, and I can see the access level thread local, I can access that. That's not a problem. Now the problem with that is I have unconstrained mutability of that. What does that mean? It means that the thread local has get and set on its interface. There's no separate interface for read only and write only. right? So if I can read to it, I can write to it. So I can do something dodgy like this, where I can set something, elevate my permissions to admin and do the thing, and then set it back to its original value. And I've never written code like that, I assure you. But you could.
I see it on the screen.
Thank you, Jim's found my dirty secret. I have written code like this more than once. Because hey, it's a way around. So you can unconstrained mutability. I don't know who's touching that thread local. I don't know why. As long as they can see it, they can get access to it. So sometimes people use them as a way to return more than one thing from a thread. You can, like anybody can poke a value into there. It changes the runtime of your application. So that's one problem. The other problem is there's no specific lifetime for these. As long as if I set something on a thread, it's on there, and I put that thread back in the pool, and I get another request, that value is still on there. So I can pollute future work by doing this. So as a developer, we have to call remove when we're done with that value. We have to remember to do this, and this is a source of a lot of bugs. The other problem is inheritance can be expensive. So if instead of using a thread local, I use an inheritable thread local, anytime I create a child thread that has a thread local associated with it, I'm getting a copy of all of those variables into my child thread local, the child thread. And this can be expensive. It's also buggy if I'm using the thread local as a thread safe cache. Now I've got two threads using the same object. So you probably maybe have run into this one. I haven't used inheritable thread local very often. It is it's convenient, but it's also a good way to shoot yourself in the foot. So scope values help by basically doing the opposite of all these problems. Their values are mutable. Once I set it, I can't change it. I can redefine it for my child scopes, but I can't change it for my scope. There's a defined lifetime. It runs within a specific scope, and I'll show you what that means. And then inheritance is cheap or free because the values that are stored in there are immutable. I can share that value between child threads. I don't have to make any copies. They just refer to that same thing. I don't have to do a reference copy. Again, this is in preview. You'll have to call enable preview if you want to use it. And let's see what these are. Okay, so to define one, I'm going to say public, static, final, scope value, string, and we'll say, call this username. That's it. Okay. Now, to use this, I'm going to execute some code within a scope. So I say scope value. And I say .where username is target. And I can do as many of these as I want. I can add other wheres to that, and then I say run. We'll redefine a child function in a second. Now when I say run, it's not running in some other thread. It's just incidentally called run because I'm passing in a runnable. You can also pass, what else can I pass? Callables, and then suppliers. So I can say get with a supplier or call with a callable. Okay, they all run in this same thread. So it's just called run. Don't assume that there's any threading here. So if I have my child function, I can say if username is bound, I can test whether any variable has been bound to that, because it's possible to get it and not have been bound. And we'll just say if it's bound for now. Okay. So what this is doing is it's creating a scope value. It's binding username to TriJug to username, and then it's running the child function within that scope. And so I should get the answer that I'm looking for. I should just get try jug as the answer, and I do. Now that's not all that interesting because it's one function away. You could have just passed that as a value. But imagine you've got your code and then a bunch of frameworky code that you can't change, or maybe it's a lot of different function chains you call, and then like far away from where you define that scope value, you want to use it. You don't want to add a string for username to every function along that line, even if you could. And in a lot of cases you can't. Like if it's Spring Framework code, you can't, right? So let's mimic that. Let's go into our very important data and say if example dot username that is bound and example dot username. No, we'll just do it this way. We don't have to do it is bound. We can just say get or else some default value, and we'll just say empty string. This is demo code, and we're not that picky. Equals. So if it's tryjug, if we can detect that the username is tryjug, we will return the best Simpsons character, who's the first one in the list. This is also really nice. Get first, I think came in Java 21. So instead of saying data.get.0, you can just say get first.
Nice.
Closer and closer to Kotlin every single day. Guess which side I land on. Okay, so put it in your mind that so like the important part of this code is that you're going to get the best Simpsons character. So I want if you've watched The Simpsons, I want you to put in your head what you think the best Simpsons character is. Okay, because there's only one right answer to this. So we run child, and what's going to happen is we'll say instead of doing something useful here, we will we'll print out the thing. So what this is mimicking calling framework code. So child doesn't even know that this exists, that this exists at all. And in fact, we'll run it without that first. So we'll see. We'll just get some random Simpsons character. Let us do that. Okay. There's a way to do it without anything. I just forget what it is. Okay, so we'll run this, and we'll get the single best Simpsons character, who's obviously Johnny Typers. And I'm not telling you why. Thank you, Jim. So I like this because now I can, if I want to, I can create a child thread in here. So these work really well together, by the way. Again, we are not writing Kotlin, so I need the new keyword. And if I say scope.fork something. And we'll play with this more in a second. I don't really care. Really? Fine. Again, don't do this at home. We will print the answer. Okay, so what are we doing? We're creating a scope value. We're creating a child thread, which should inherit that value. We're calling print something, and we're returning the value. So this should return Johnny Tight-Lips again, the single best Simpsons character there is. It's an important part of this lecture. But we can also change that. Now I can't change it for me because I can't change it in here because we're running this, and I can't change it in here. Like I can't say username, .set or anything like that. But what I can do is I can do this. I can run this. So we'll say tryjug with an exclamation point because we are all very excited. And we can say run. This will be a test of parentheses will hold, because I always screw this up. And we probably need this, right? I can never tell when I need to. Seriously? This touchpad down here is so sensitive. No. Alright. Again, don't do this at all. There are better ways to do this. So we should see some other random Simpsons character because I'm redefining my thing, AutoMan. That's the name of the bus driver. I'm redefining it for this scope here. And I can add other ones. If I had another different thing, I could add that there. So I think this is nice that they play well together. I don't have any penalty for doing that, and all the child threads get that by default. So a couple things to remember about scope values is they're useful anywhere you need to pass data one way. So if you're not using this as a way to just kind of poke values into a thread-safe pool, this is a great thing to do it. And then try to migrate to scope values away from ThreadLocal, again, if you can, again, or away from both of these. If you can use some other structure to limit concurrency other than ThreadLocal, try to do that, like a date formatter. There's thread-safe date formatters. You don't need to put simple date format in a ThreadLocal anymore. Things like that. So remember, both of these are in Java or in preview. You're going to have to call enable preview on it. And nothing you like is going away. These are all additions. So these are one of the things I really love about the Java improvement process or the Java enhancement process documents is there's a section at the top saying goals, this is what we're doing, and there's a section below it that says non-goals, this is what we're not doing. I am explicitly acknowledging that this is something people care about and I am not doing it. I put this in every one of my design docs. I think this is the greatest thing in the world of acknowledging that something is a thing, but I don't care. So from the non-goals section of all of these, it's not a goal to remove platform threads in favor of virtual threads. It's not a goal to replace executor service or future. They're still there. And it's not a goal to remove ThreadLocal. Okay, so everything I showed you, the bad versions, they're all still in there. If you still want to do it, that's fine. If you want to compile code on Java 22 or 23 or whatever, these things will all still be there. Just because there's new things doesn't mean that the old things are going away. If you want to know more about the Java 23 code, when it comes, like if these things come out in Java 23, I've hand arranged this set of dots for you, okay? That'll take you to the Java 23 release page. If you want to know what's going on in Loom, again, hand arranged, just for you. This is the Project Loom wiki. It's like basically what you think a wiki written by a bunch of old developers look like. It's pretty dry. However, it's got some really good presentations. It's got a lot of documentation on the whys and hows and a bunch of stuff about fibers, which is what virtual threads were called originally for years before they switched the names. The best part about it is there's a mailing list. Now it's again, old school developer mailing list, so it's like all text from a listserv, old school. I love it. And you can go and read all the threads that they have. So you can see every commit that is made under Project Loom to the JVM, and you can see them discussing issues like when to release things or how do you get around things or design discussions. It's fascinating. So you can go do that. I'm here to stick around for any questions that you might have, and I want to thank you very much for your time and for listening and for being here and all. Thank you. 6 minutes. Okay. Questions?
So what happens when you pool the virtual threads? I mean, why do you say that it should not be?
Because they're free. You don't need, so the reason you pull platform threads now is because they take time to create and they're taking up an operating system thread. But a virtual thread, it's basically free to create them. You don't need to pull them. There's an infinite number of them. Like you'd never pull like some run-of-the-mill object that you create a lot of in your system, like a string. You'd never pull that. You'd let the JVM worry about it, like interning and all that nonsense. But like it's a regular, normal, like a list, you would never just like pool lists and then like empty them out and create them. Think about virtual threads the same way. If they're free, I don't need to pool them.
So you were showing an executive service that kind of for virtual threads. That's again like a pool, right? But
it's an executor service. you're thinking of it as like a pool because all the other implementations are pools.
Right.
But really what an executor service is I am giving you work, please do it. And when I say, here's a fixed thread pool, or here's a new thread per whatever, I'm telling it the method that I want it to execute that work on. But I'm not telling it to pool things explicitly. It's not a pool, it's an executor of work. Now, if I say, here's a new virtual thread per task, I'm telling it, I don't want you to create anything. I want you to take this work, create a virtual thread, do the work, throw it all away. So, yeah, it's not really a pool. Questions? Yes?
What are some examples of times you really want to just find and use virtual threads? Like what are the times?
So, a lot of things right now have issues with virtual threads. So there's mainly like if you have a JDBC driver, if you really are using threads as a way to limit concurrency, like with a JDBC driver or something like that, it's probably a good idea to like stop and think about whether your driver really supports virtual threads, because I don't know the one actually does outside of the RTDBC ones, which are the reactive database drivers, I'm sorry. And they even might not. So that's a case when you would not want to do that. There's an issue with virtual threads in Java 22 called pinning. So the diagram that I showed where go up 100. There's 155 slides, and it's like right near the beginning, so you gotta bear with me. Yes, we can do this. I used to play drums, so this is how I can do this again. That one. Now I don't even remember what I was talking about. So pinning. So if virtual thread 1 you call synchronized, or you're calling a JNI method, so a native method, in current implementation of virtual threads, it has problems unpinning. It has problems unmounting those, so you can't unmount them. It'll pin the carrier. It'll pin the virtual thread to the carrier until that synchronized scope is done. You can get rid of that by using a lock instead of a synchronized method, or just not calling JNI. Now, landing in Java 23 are fixes for most of those cases. So that don't use virtual threads use case should go away in favor of using virtual threads. But yeah, again, it's like if things are written in a way that assume a thread is a limit on the unit of concurrency, then that's probably a bad place to use virtual threads.
It just sounds like, this is interesting, it sounds like what you're saying without saying is serverless.
Sure, you could view it that way. Yeah.
I mean, the ultimate thing, there were a few times I actually thought, this sounds a lot like serverless event architecture, that kind of stuff. Are they planning to go towards that? Or?
I don't know. But I mean, the reason we like serverless is because it's basically just, I want you to call a function for me, right? I don't care about any of the other things about the setup or anything around it.
Exactly.
Whereas this, I think is similar but slightly different. Like now, if I have a unit of concurrency and a scope that is free, and a scope, a structured concurrency scope that I can basically assume I will always get the right behavior, I can do concurrency in a lot of different places that I wouldn't have done those before. Right? So a lot of places where you would think, boy, I could do these two things at once, but I'm not going to because it is such a pain in the neck. Now you don't really have an excuse. You can go and do those things. But yeah, it's a little different than serverless, but yeah, I see where you're coming from.
How is it different?
Well, you get the whole JVM around it, right? I mean, it's just in this case, I'm just running simple functions, whereas serverless is like, I'm packaging up, a function in the entire runtime, and you're not seeing a lot of the runtime.
Yeah, but could you use like JLink and J?
Sure. Yeah, you still get
break it down.
Yeah, you could. Yeah.
Yeah, but would that make it a lot less expensive?
In terms of memory and
disks,
disks,
sure.
sure.
Serverless function. Just curious.
I guess so. Yeah. I don't know. I mean, I'd probably just put that in a base layer and not worry about it. But yeah. I haven't done serverless with Java because I just do other things. I do JavaScript or Python.
Yeah, I just been coming to my
Yeah.
mind, listening to
No, but I see where you're going with it. Yeah, I mean, it's like if you're thinking the VM is like a cloud provider, then yeah, you're submitting work to a single thread that does one simple thing and you're waiting for it to finish. But sure, but I think they're quite different.
And I know Java 9 introduced something to reduce like the jar number, jar files, and everything.
Yeah, that's
like
the JLink stuff we were talking about. Yeah, but that's in place of JREs. So you don't have a JRE anymore. You can build your own. Right? But I think these are a little bit different. Questions?
So what do you think will be the adoption of the virtual threads for the frameworks? This is just starting, right?
Yeah, so Spring Framework already does this. Like they've already taken several places and started using virtual threads. Spring Framework is usually the first in a lot of these. You know, I didn't put it in the talk, but Brian Getz, who's the Java language architect at Oracle, has said he thinks this will be the end of reactive. There's really no reason to use reactive. Yeah, exactly. Yes! I can't stand reactive code. It's just creating complexity, and you're trading it off for back pressure that nobody needs. Very few people need. And so I think if I can get basically free concurrency and structured programming like semantics with it, and not have to do callback heck and all these other things, I'll give up back pressure for that. I've rarely seen a use case where back pressure really makes a lot of sense. And so I think that's where you'll see those, where people jumped on reactive and thinking, boy, I'm stuck with this now because I've done it, but it's not worth the trade-off. The complexity of it is not worth the trade-off. I think you'll see that new projects from that group swing back to using structured programming and virtual threads and structured concurrency. That's just a guess. If I had to guess, that's what it would be. But I'm really bad at guessing. So. Any more?
Do you know how it would manage a CPU-bound process with more threads than capacity?
That is a really good question. So Jim's asking about, what if you have CPU-bound work?
Yes.
This isn't great for CPU-bound work. It's really great for I/O work where you have a lot of break, like you have a lot of waiting. CPU, if I want to put some work in a virtual thread that is very CPU intensive, you're not going to get mounting and unmounting to the extent that you would if I was like calling a bunch of APIs or waiting for a bunch of socket connections or disk activity or things that you traditionally wait on. CPU, you never really wait. Right. So yeah, good question. I should address that in the next version of the talk. That's a really good point I should address. Cool. Questions, comments, concerns?
If you have a number of virtual threads that are, various stages, they become ready at the same time.
Yeah.
Is there a way to prioritize them and say that I need this one to go first?
I don't think so. I think that's just the same as any other. I don't know that you can even set a priority on this.
Don't you said we put at the beginning when we said the thread?
I mean on virtual threads. I don't know. I don't think you could set a priority.
Just a standard fork join forward.
Yeah. Well, yes, kind of. So you can't, under the covers, you don't care. You're telling Java, I don't care which carrier this goes on or how or when. So I'm not sure that you can say this one is better. This one is more important than that one if they become active at once, because the JVM is going to put them on whatever carrier thread. It could put them on different ones every time. It doesn't really, you don't have any control or say over that. So
I had a scenario where I wanted the one that was closest to being finished.
Oh,
Continue
yeah, I
first.
can see why, yeah. Yeah, I don't know. I don't think you can do that. But that's a good question. We'll think about that. I don't think you can. That'd be fun if you could. It'd probably be more complicated if you could, don't you think?
Well, I did it with
Sure.
queues.
Yeah.
And I checked the most advanced queue first before it did that first.
Yeah. No, that's a good solution to that, but I'm thinking with virtual threads where I don't really have control over the concurrency, I'm not sure how I would tell it, like this one's nearly done. Yeah, that's a good question. How I do that in a simple way, basically. I don't think the API certainly doesn't support the snap, but I don't other than just pure priority, which it doesn't appear to have.
You can't move a virtual thread from one scope to
No, you can't. So that's the other problem with the futures is I can pass that future to anybody, any other thread, and it can cancel my work. It can outlive everything, right? Whereas these scopes, these are uncancelable. The scope takes care of it. I can't, even if I pass it to another thread, there's no bearing on it. It can't interact with it in a meaningful way. Cool. Anything else? Alrighty, thank you very much. I appreciate your attendance.